So this, so all of this that we've talked about with this HRTEM, again, relies on us being able to produce a diffraction pattern like we saw in diffraction mode. So this is just a similar image to what we saw. And so the setup is slightly different. So what we effectively do is we're looking, we set up the optics of the TEM such that instead of looking at the real image, what we're looking at is we are basically converging on the reciprocal space layer, and we are projecting that onto the screen so it's enlarged. So effectively, this diffraction pattern, obviously these features are very small, and so the real reciprocal space is quite a bit smaller. So we're projecting it and magnifying the diffraction pattern such that we can see it. And so that's what we're doing. We're magnifying this reciprocal space lattice on this back focal plane of the TEM. And so that's why we're able to see it on the image. So we basically configure it slightly differently such that we're producing this diffraction pattern on the back focal plane. All right. So this is known as this is known as selected area diffraction, or sometimes SAD. You might also see it as SAAD. I've seen a couple different abbreviations, but it refers to selected area diffraction. And so this is when we produce that diffraction pattern. So we can obviously use this to set up the image for diffraction mode, right? We saw that kind of contrast. So that's one area that we can do it, and that's what we talked about before. You can also use that for high resolution TEM or phase contrast. So SAD is a way of setting up that imaging mode, because we need to be able to arrange the objective aperture for those modes. However, it's useful on its own because it gives us crystal structure analysis capabilities. Because we're looking at reciprocal space, that tells us about the diffraction. It tells us about the crystal structure of the material. So in a kind of comparison to the two, scattering is different because in SAD and TEM we're scattering by nucleus, and then it was actually shell electrons in XRD. The wave path in XRD typically are reflection, so the type of the type of diffraction we saw was reflection. Here it's transmission. And again, we emphasize this diffraction angle, right? 0 to 180, that was pretty typical for XRD. However, we're talking about small, less than 2 degrees is usually what we're talking about. The intensities in XRD actually tend to be pretty low. Here, they're quite a bit higher. However, the precision of XRD is very high. We can get very specific numbers, precise numbers for B spacings and therefore lattice parameters. However, the way that we image and look at the diffraction planes in SAD means that the precision's a lot low. So if you calculate a D spacing in TEM, the precision of it is going to be a lot less than what you have in XRD. So there's a lot more kind of error associated with it in this mode. However, the main difference, which doesn't appear on this table 3.4 in your textbook, the main difference is XRD in the way that we looked at it looks at the bulk material, right? It looks at a very large area. If you were in the lab, you saw that how large of an area that could be. However, in TEM, right, we're looking at a very small selected area, which is where it gets its name, of the specimen. And so we can do more focused diffraction studies on very particular areas. And so if you're asking yourself why we would want to do that, well, if something has multiple phases or particular regions, for example, an inclusion, or another secondary phase, we can get diffraction of just that particular area, or we can look at the other phase, right? So we can select our area and look at differences in diffraction, and that can also be orientation. If we have a grain structure and there's multiple grains and they're all at different orientations, we can study that different orientation with this type of diffraction. Whereas XRD, we're getting kind of an averaging of that whole bulk material. All right, so these diffraction patterns that we see in selected area diffraction, or SAD, correspond to the reciprocal space. And we've talked about the reciprocal space in the past, but just as a refresher, each spot corresponds to a real plane. And the information between the transmitted beam or spot and the diffracting spot, that vector in reciprocal space, if you take, that basically gives you the reciprocal of the interplanar spacing. Since we are in this arrangement with magnifying the reciprocal space, then the geometry of the setup will correspond to a much larger vector so that we can see it, and we can measure that and relate it back to the interplanar spacing. So we also talked about how in the past, those spots that are diffracting are on the Ewald sphere, right, from Bragg's law. They're on the surface of the Ewald sphere. And that's going to, the surface of that sphere is related to wavelength, and the wavelength here is a lot different than with X-rays. So the first thing that we've already calculated this, we know that these diffraction angles that we see are very small. And so if we take Bragg's law as a starting point, because this is diffraction, it still applies, we know that these diffraction angles are very small, again in that range of 0 to 1, sometimes up to 2 degrees. We know for sine theta, if we're dealing with these small angles, then sine theta can actually simplify to just theta. That's a simplification that's valid for small angles. So we can already kind of make a simplification of Bragg's law. Additionally, the geometry of the TEM and the camera, where basically the image is taken, can be added into this equation to give us a basic equation for electron diffraction. And so when we talk about image geometry, we're really talking about the specimen and how far away the image is, right? Because we're basically projecting this reciprocal space onto a much larger or much magnified on the actual image plane. And so R is a magnified version of the vector between those two spaces, and it gets larger as this length, this camera length between the specimen and the image plane, gets larger and larger. So for TEM, a typical camera length is on the order of 1 meter. So if you need a sort of quick back of the envelope calculation, you can use L equals 1 millimeter for 200 kV. So if you've ever looked at the TEM and wondered why they are so tall, you can think of this, right? Between the specimen and the image plane, we need about 1 meter to be able to get the R values in which we can measure the distance between the central spot and the reciprocal spot. And so in doing that and putting in the camera length with relation to R and G here, we can rearrange or simplify this expression to get kind of our basic equation for electron diffraction. So that is lambda, the wavelength, in this case of electrons, multiplied by the camera length, is going to be equal to R, which is the projection of that vector, times the d-spacing. So this allows us to calculate the d-spacing, or d, by knowing the wavelength of electrons, if we know the accelerating voltage, the camera length, which is going to be tied to our setup, and then the measurement of R, which we do from the SAD image. All right, so another thing we have to kind of grasp when we're talking about these SAD or SAD images is that these reciprocal lattice points, the points we see, aren't tied to every single diffracting plane in this crystal, because only the diffracting planes that are a member of the zone of whatever the incident beam is. So in this case, the incident beam is along the 001 direction. And so we know from the Weiss zone law that 100, 010, 110 are all members of the plane. So they have the 001 direction within them. And so it turns out that only planes that are members of the zone will diffract. So if our beam is parallel to the 001, only planes that are a member of the zone will diffract. So this is a real central part of diffraction TEM, is that we only see diffraction from those that are members of the zone, and this tells us that the orientation matters, right? So even though XRD or just general diffraction would tell us we have a certain number of diffraction planes, only those that are in the right orientation, governed by Weiss zone law, will diffract. And so we wouldn't expect others in this pattern if they're not members of the zone. So that's why we introduced that zone law, because that's very important for diffraction. So orientation really matters. And so we have to keep that in mind when we're looking at these patterns. The other thing that's useful to realize is that, the electron wavelength is very small. We've seen that from the table in the book. And therefore, since it's a reciprocal, the Ewald sphere surface, the circumference, is very large because the radius is very large because this is small. And therefore, we can often approximate that surface as being flat. And that's in comparison to XRD. So I recommend you go back to when we talked about Ewald sphere. I made the comparison between electron diffraction and X-ray diffraction. And you can see that I have some images there showing the relative size of the Ewald sphere that can be helpful in that relationship. Another effect that I just kind of want to go over when we talk about SAD or SAD is that these crystals are often very thin, what we consider thin plates. And thin plates are a lot like small crystallites when we did XRD. They can actually give some distortion. So instead of seeing a single spot that's symmetrical, so it's a circle, instead we actually see more of an elliptical, or what looks like it's been elongated in one direction. And because of that, the Ewald sphere often will intersect more diffraction spots than we would initially expect. And if you're wondering kind of why they elongate or produce these rel-rods, as they might be called, so these kind of spot patterns, it's the same concept that we talked about in XRD, where a small crystallite will cause that peak to broaden because we get diffraction over a wider range of angles. And it's the same thing here. We're getting elongation in one direction because of this thin plate. A thin plate meaning it's very small crystallite in that one direction, and therefore we get elongation in that one direction. So if you're seeing these rel-rods, it's a relationship with these thin plates that we see in XRD. But again, same concept as crystallite size or the shear equation that we talked about in XRD. All right, so I just mentioned the zone axis and how we have to have the beam parallel to the zone axis in order to get diffraction of members of that zone. So if you think about this, proper alignment is going to be important, because if we have a specimen and then we have an incident beam coming down in a certain orientation, we need that incident beam to be parallel to the zone axis in order to get strong diffraction. If we're off, then diffraction will be very weak or non-existent. And so those single tilt and particularly double tilt sample holders are very important in order to get this high symmetry that we have, in order to get the beam parallel to that zone axis. So tilt, when we're talking about these diffraction based techniques like SAD or phase contrast, really rely on tilt of the sample in these sample holders. All right, so all of this together, these diffraction patterns, we know that we can get interplanar spacings from the distances between the transmitted spot here in the middle and the spots, diffracting spots. Those give us information on interplanar spacing. And each one of those is going to be tied to a specific plane, as you can see from the labeling here. And just like we did in XRD, if our crystal's not known, if it's unknown, then these spacings with their values can be used to index an unknown specimen, right? So having all of these different spots and the distances away and the orientation to the central spot, which is covered up here, and you can kind of see it here, then these angles and distances can actually be used to index a crystal and also tell us about the orientation. So what is parallel to the beam. And so we can use these diffraction patterns to index just like we did in XRD. And so in the next modules, we're actually going to go through how we do that and an example of that as well.